A fuel cell is a device which converts chemical energy into electrical energy. And the attraction of a fuel cell is that in principle it can perform this conversion at comparatively high efficiency. There are different kinds of fuel cells. The most popular fuel cells are PEM fuel cells, polymer electrolyte membrane fuel cells, and SOFC's, solid oxide fuel cells. The primary difference between those two fuel cells has to do with the nature of the electrolyte membrane. In one case, in a PEM, the electrolyte membrane transports ions only and forces the electrons to go on the outside. In a solid oxide fuel cell, the predominant charge carrier mechanism is oxide ion conductivity. So in one case we conduct protons through the electrolyte membrane. In the other case we conduct oxide ions through the electrolyte membrane. The way we make our fuel cells is we have adopted thin film processing methods. Particularly one methodology we have been adopting in our manufacturing processes, atomic layer deposition. The beauty with atomic layer deposition is that you literally control the deposition of the material you put down at sub-nanometer scale. One lattice dimension ranges between 1/3 and 1/2 nanometer, and being able to control it allows to make very precise and, if you want, designer fuel cell structures where you can build in gradients, you can custom tailor the anode, you can custom tailor the cathode. So it allows you not only to build very advanced electrolyte membranes, it allows you to build very advanced anodes and cathodes, which naturally can be tuned to a significantly higher performance than traditional fabrication processes would allow to do. My interest in fuel cells has been to bring down the operational temperatures of solid oxide fuel cells. And then the way we accomplish that is by making the electrolyte membrane inside the fuel cell very thin. The thinner the membrane, the lower the ohmic resistance. If you have lower ohmic resistance, you can afford operating the fuel cell at comparatively lower temperatures. Traditional fuel cells have been operating at 700, 800, 900, even 1,000 degrees centigrade. And by making the membrane as thin as we can do using nanotechnology, we can operate the fuel cells as low as 300, 400, 500 degrees centigrade. There are many major challenges in implementing fuel cells on a large scale. These challenges are different for stationary applications and for mobile applications. For stationary applications, the challenge is obviously, where does the fuel come in the first place? Are you going to use natural gas, which is certainly a candidate, but then the issue of reformation becomes key. If you talk about mobile applications, then the hydrogen infrastructure becomes key as well, because you need to access hydrogen throughout the country wherever you drive. And another key challenge is in the fuel cell design itself, or the fuel cell structure which we built today. Certainly for all the low temperature fuel cells we use platinum as a catalyst. And platinum is obviously an expensive material which with limited supply in the future. Chances are we're going to run out of platinum before we'll run out of oil. The future of fuel cells is ultimately linked to the supply of the fuel. What kind of fuel infrastructure which we can take advantage of. And it's very difficult to make reliable predictions. I'm just not in a position to predict what the future is going to hold in this area. At the same time, I do believe the community is very interested to explore more efficient energy conversion schemes, and fuel cells is clearly one opportunity. So I believe you will see a lot of experiments over the next few years, and people will find better energy conversion schemes, and clearly fuel cells are a prime candidate.